Today's lecture will be on weathering processes and products. So let's get started. We can group weathering processes into two main categories, mechanical weathering and chemical weathering. Mechanical weathering is looking at the physical breakdown of rocks from larger pieces into smaller pieces. The products of mechanical weathering are solid particles of rock, clastic materials that we can categorize based on their size, with silt being the smallest and boulders being the largest. Next, we have chemical weathering, which again is breaking down rocks, but this time through chemical processes or chemical reactions. So the products differ in chemical weathering, and instead they can either be solutes, small particles dissolved in solution, or colloids, which are similar to solutes, but it's including particles of organic and mineral substances, very, very small, ranging in size from 1 to 100 nanometers. We'll start out looking at 5 different mechanical weathering processes: unloading, frost action, heating and cooling, swelling and shrinking, and salt crystal growth. Unloading is a mechanical weathering process in which we have one body of rock that at one point in time was buried under a lot of material which exerted a great pressure on that rock, and through some process that overlying material was removed and the underlying rock is now expressed at the surface. So the pressure has been reduced on this rock body. With this reduction in pressure comes an expansion of the grains within that rock. And as the grains within the rock expand, we have fractures and joints developing. What's particular about unloading weathering is that these joints develop parallel to the surface, creating lines of weakness. This is really common in igneous intrusions, especially when they're uplifted to the surface. A more specific term to describe unloading is exfoliation, where the fractures that occur parallel at the surface create this line of weakness where the superficial rocks now break off in thin sheets. Unloading or exfoliation weathering is dominant in Yosemite National Park. And so you'll see these igneous intrusions that have been uplifted to the surface have very rounded surfaces on the rocks, and that's due to this exfoliation weathering. Frost action. It's a very simple idea. If we're looking at water penetrating pores and fractures within rocks, when water freezes, it expands because it's a polar molecule. Let me just get my pen, and I will choose this color. So here I have a diagram of water in its liquid state and its solid state as ice, and you can see that the space in between the molecules expands when water freezes. So that means frozen water takes up more space than liquid water. So during that expansion, as the water is freezing, it can open up the cracks even more than they already are. So it's this expansion and contraction that's occurring with frost action. We'll sometimes refer to these as freeze-thaw cycles, and this is a very dominant process in colder climates. Sometimes it can also be referred to as hydrofracturing, where we have water filling pores expanding rapidly, exerting a new pressure called cryostatic pressure. So that term cryo, the prefix cryo, is frozen. And this pressure is transmitted through the entire rock body, and it can cause severe fracturing to occur. Next, we have thermal weathering, sometimes called thermoclasty, where we're looking at heating and cooling. Again, we're looking at expansion and contraction. So similar to frost weathering, but this time the mechanism causing expansion and contraction is heat. Rocks have low thermal conductivities, which means they're not good at conducting heat away from the surface. This would make them a good insulator. So if the surface of the rock gets hot, that heat energy does not make it to the middle of the rock very quickly. What happens is we have this difference in temperature from the surface to the center of the rock body, where the outer grains become much hotter than the inner grains, and then the hotter grains expand more than inner grains. And what happens with this thermal weathering is we get flaky materials breaking off at the surface, and over time, the original rock body gets smaller and smaller. Next, wet-dry weathering, specifically looking at materials enriched with clay minerals. Smectite and vermiculite are a couple of examples of clay minerals, but if you see a mineral with this ite suffix, I-T-E, that tends to indicate that it's a clay mineral. So smectite and vermiculite are some of the most common clay minerals. And clay absorbs water, so it swells when it's wet and it shrinks when it's dry. Again, we're looking at expansion and contraction. First, we looked at frost weathering, so that expansion and contraction is because of ice. Then thermal weathering, it's due to heat. And now in wet-dry weathering, it's due to water. Some sedimentary rocks like mudstone and shale have a high percentage of clay minerals, so they undergo wet-dry weathering very frequently. When the rock is wet, it expands and forms little cracks, micro cracks. When it dries, it shrinks and the larger shrinkage cracks form. So this photo is looking at the shrinkage cracks. That was a bad arrow. Sorry. I don't have a mouse. I'm using my touchpad. Salt crystal growth is dominant in coastal and arid regions. So coastal regions, the salt is coming from the ocean. In arid regions, the salt is coming from high rates of evaporation. So again, the salt crystals grow when high salinity water evaporates. So say we have water spraying some rock surface. That water evaporates, it leaves behind the salt crystals, and the salt crystals will grow in the joints and the pores. They widen the cracks and cause granular disintegration. Sometimes it's called haloclasty as well, but again, we're looking at this expansion. So the salt is widening pre-existing cracks in the rock. And over time, individual granules are pushed apart, so they're no longer one cohesive unit. That's it for physical weathering or mechanical weathering. Now we'll move on to chemical weathering. And okay, that chemical, that says chemical. Oops, and that's an H. Okay, sorry. Chemical weathering processes. Solution, oxidation and reduction, carbonation, hydrolysis, and chelation. Solution, we're looking at molecules dissolving in a fluid. Dissolution is looking at the dissociation of molecules into their anions and cations and are suspended in solution. So dissolution is the process of dissolving molecules in water. Once that water contains an abundance of dissolved anions and cations, we can call it a solution. If the solution becomes saturated, we might have solid molecules precipitating out of that fluid. Solubility, the ability to dissolve, varies for different minerals. So some minerals dissolve more easily than others when in contact with water. The most soluble molecules include salt, or halite is the actual mineral name, NaCl, sodium chloride, potash salt, potassium chloride, gypsum, which is calcium sulfide with water. So these are most soluble minerals. They don't require acidic water to dissolve. They'll dissolve in neutral water as well. But acidic water is capable of dissolving minerals that do not have a high solubility. And so acid rain can really contribute to high rates of dissolution in rock bodies that wouldn't typically dissolve easily. Next is hydration. We're looking at when minerals absorb water molecules on their edges and surface without changing the chemical composition of the original mineral. In salts, we have water incorporated into the crystal lattice. So, for example, anhydrite is a mineral, calcium sulfide or sulfate. When it absorbs water, it becomes gypsum. So we've incorporated water into the crystal structure within this chemical formula, and we actually now have a transition from one mineral, anhydrite, to a different mineral, gypsum. The absorption of the water also causes the volume to increase, which is similar to the mechanical weathering process of wetting and drying. That's occurring because of hydration. But this specific hydration is looking at this actual shift within the chemical composition of a mineral versus wetting and drying is simply expansion and contraction. Oxidation and reduction, looking at the transmission of electrons from one molecule to another. Oxidation is when a molecule loses electrons. Oxygen is an oxidizing agent, which means it pulls electrons away from molecules, very common in iron, manganese, sulfur, and titanium. This oxidation reaction creates rust. So we actually see a visible substance form at the surface. Reduction is now the opposite of oxidation. It's the gain of electrons by a molecule. And this is occurring in areas deficient of oxygen. If oxygen is present, oxygen will oxidize metallic molecules. But in areas deficient of oxygen with a high concentration of anaerobic bacteria, we'll actually see the opposite occur, where molecules will absorb electrons or gain electrons. When reduction happens, we don't get rust, we get something called glaying, which is when our chemically weathered minerals take on this grayish, cloudy color. Redox potential, which is symbolized with this EH, measures the ability of a solution to supply electrons to an oxidizing agent or to take up electrons from a reducing agent. So redox potential, we are analyzing whether a solution is going to oxidize a substance or whether it's going to reduce a substance. Positive EH, we're looking at oxidizing. Negative EH, we're looking at reduction. Carbonation now is looking at the formation of carbonic acid, which is dihydrogen carbonate, when water mixes with dissolved carbon dioxide. So we're looking at water, carbon dioxide. Here's our chemical formulas. We have carbon dioxide plus water creates this carbonic acid. Then calcium carbonate plus carbonic acid breaks down and creates this what's called calcium hydrogen carbonate, and this molecule easily dissolves in water. So we have two chemical reactions with the final product having very high ability to dissolve. Carbonation is dominant in the weathering processes of limestone and dolomite. Limestone and dolomite are mostly composed of calcite, calcium carbonate. Limestone is 99% calcium carbonate. Dolomite has a slightly lower composition or slightly lower concentration of calcium carbonate. So if we have carbon dioxide present in water, that will create our carbonic acid, which will then work to dissolve calcium carbonate. Hydrolysis is, again, looking at water. Water splits into hydrogen cations, so hydrogen plus, and hydroxyl anions, OH negative. And these cations and anions will react directly with the silicate minerals. Silicate minerals tend to be highly resistant to weathering, but hydrolysis is one chemical process that can work to break down our silicate minerals. Hydrogen plus is exchanged with a metal cation in silicate minerals, either potassium, sodium, calcium, or magnesium. And then this released cation then bonds with the hydroxyl. So we're taking an atom from a silicate and giving it to this hydroxyl, which is going to change the composition of the initial silicate material. Desilication is a more specific term for hydrolysis, the process by which silica is removed from a compound. So we made it through our different chemical and mechanical weathering processes. Now we're going to look more at weathering environments and associated products. We can distinguish between two types of weathering environments: weathering limited environments and transport limited environments. Weathering limited environments means weathering is limited. Transport process rates are higher than weathering rates. So that means any material produced by weathering is removed and regolith or soil is unable to develop. So weathering is limited because transport is occurring at such a high rate. In these weathering limited environments, rock composition and structure will determine the resulting surface forms. And we end up getting cliffs, pillars, rock basins, tuffoni, and honeycombs as some examples. We are going to look at each of these individual landforms coming up. Next, we have transport limited environments, where it's the opposite now. Weathering rates are higher than transport rates. So we have more weathering than transport, which allows for a regolith or soil to develop. Forms are now shaped directly by weathering and mass wasting. The materials released by weathering can continue to weather and break down into smaller and smaller particles. Transport limiting environments, we end up with thick regolith and soil, duracrusts, and hardpans. We're going to start out looking at weathering limited environments and the landforms that are common in these weathering limited environments where transport rates are higher than weathering rates. Cliffs and pillars. We've talked about cliffs a lot, but it's a steep rock face. Sometimes cliffs may have joints, and the joints within the cliffs are a plane of weakness, and they'll be more susceptible to weathering. So the cliff can break down rapidly if it has a high concentration of joints within it. A pillar is tall, narrow, isolated rock structure. So this whole area can be considered a cliff face, and this isolated segment can be considered a pillar. Or we could even expand it down to here. Pedestal rocks are cliffs or pillars that experience undercutting formed by either or a combination of the presence of softer rocks at the base of a structure. So we have differential weathering because The cap rock is more resistant to weathering than the base rock. Abrasion by wind-blown sediment near the surface. Salt weathering caused by capillary action of soil at cliff base. Increased moisture at the base of cliff that enhances weathering. So here's an example of our pedestal rock. So we have a large cap rock that's much larger than the pedestal that it stands on. So this rock unit is less resistant to weathering than this rock unit. And so we end up with this top-heavy structure. Next, we have rock basins, also called potholes. Potholes are just a closed circular or oval depression. They can be a few centimeters wide to several meters wide, and they tend to form on flat or gently sloping surfaces. So within a pothole, the floor of the pothole is fairly flat with steeper walls, and we have what looks like a saucer-shaped indent within rocks. They start out small, but if we have this small indentation, that's where water is going to water is going to end up filling in these small depressions. And over time, we'll have this positive feedback mechanism where that presence of water continues to expand these potholes, and they will get bigger and deeper. Tuffoni and honeycombs, common in more arid environments. Tuffoni are large weathering features that take the form of hollows or cavities on a rock surface. So it's almost like a pothole, except it's occurring in vertically oriented rock faces. And with a tuffoni, if we look at this cross section over here, the shape of the cavity itself has these arch-shaped entrances, concave wall, overhanging hoods, and smooth debris floors. So tuffoni are fairly large structures. They can be several meters in height, width, and depth, and you can see this example of a tuffoni in this picture and this person here for scale. Honeycombs are small tuffoni. Numerous small pits, no more than a few centimeters wide and deep, separated by an intricate network of narrow walls. Sometimes honeycombs are called alveoli. They're similar to the pockets in our lungs. And so here's an example. I don't have anything here for scale, but I took this photo in Grand Staircase Escalante, and these smaller tuffoni over here are probably like 1 to 2 inches in diameter. Joints and weathering. Just to quickly explain how joints can contribute to weathering processes. So joints have significant control on geomorphology, and their influence on landform evolution will depend on the openness of the joints, whether they're closely spaced together or they're far apart, the pattern of jointing, again, spacing, and rock type. In granite, high density of joints, meaning that they're closely spaced, promotes rapid rock decay. So where we have high density of joints, we'll have a lot of water flowing within those joints. So over time, that granite can decay from a large structure to a flat surface. Remember, granite is intrusive igneous rock with coarse crystal grains, high concentration of silicates. It's a felsic rock, and so it doesn't tend to weather very quickly. It has a fairly high resistance to weathering. Joints can change that, though. So joints could cause granite to weather very quickly. Moderately spaced joints, so joints are present still, but they're not very close together, we'll have differential weathering. So we'll have higher rates of erosion concentrated near those joints and less erosion on the faces of the rock. With moderately spaced joints, we get the rounded blocks surrounded by weathered rock or regolith. And we're going to look at some of those features. There's some different names to describe them. Those are Bornhardts, nubbins, and castle copies. Bornhardts are dome-shaped hills. It's very basic. Oh, that you can't really see that color. Let's choose orange. This is a Bornhardt. I'll put a B there. So fairly basic. We've rounded hills that form in rocks with very few open joints. So common in granites and gneisses. We have a high resistance to weathering. We don't have many joints. So we'll get some weathering, so we don't have an incredibly smooth surface, but not very fractured or jointed, so it still exists as one cohesive unit. Nubbins are hills with a bedrock core dotted with rounded residual rocks. So here's our nubbin. Here's our bedrock core, and here's our residual rounded rocks. Over time, if there's joints present in this bedrock core, the rounded residual rocks might extend within this area of bedrock as well. Last, we have castle copies. These are also called tors. So I'll put C for castle copies. So these are isolated hills with blocks of orthogonally fractured rocks that resemble castles. So orthogonally fractured is fractures that intersect at 90 degrees, so like a grid. But I'm going to try and draw the castle. I hope you're all seeing it. So castle copies or tors. We have grids or the orthogonal fractures, which you can't see from this perspective, is there's another fracture running right down there. All right, so that's what we're going to talk about for our weathering limited environment landforms. Now we'll move on to transport limited environments. And now remember, this means the transport is limited. So weathering is occurring at a higher rate than transport. And we end up with the development of regolith and soil. And we spoke about regolith in one of our introductory lectures, but to reiterate, regolith is a layer of unconsolidated rocky material covering bedrock. It includes soil, but not all regolith is soil. The distinction is that soil is capable of supporting life. This term saprolite is referring to rock that has been chemically weathered. It's not quite soil yet, it's not supporting life, so it's a type of regolith, but it's distinguishing itself from mechanically produced regolith. So this diagram showing what is regolith. This entire column is considered regolith. We have soil within this regolith column, colluvium, which is sediment that has been transported by flowing water that was not confined to a channel. Here's some solid rocks, solid bedrock particles that haven't totally been broken down yet. Some of that's outcropping at the surface, and that could be, from this diagram, this could maybe be a castle copy or a nubbin. And then beneath that we have saprolite, so we have higher rates of chemical weathering within this example. And all of that is sitting on top of solid bedrock, and we see our base of weathering. So where we transition from weathered products to bedrock, that's where the regolith ends. Oh, and here, just to point out, here is alluvium. So this term, similar to colluvium, But with alluvium, we have sediment that has been transported by flowing water within a channel. So rivers and streams and creeks will create alluvium, versus colluvium is generated when we have overland flow, or we have saturated land surfaces with water flowing as a single sheet, not confined to a channel. Rock debris will form in our transport limited environments. We have three different types of rock debris, or three main categories of rock debris: talus cones, debris cones, and block fields. Talus cone, we've talked about talus already. We're looking at an accumulation of rock fragments that fall from steep rock faces after loosening by weathering. So talus cones originate from a mass wasting process known as rockfall. We're going to talk all about that in our next lecture. Talus is composed of larger grained particles, cobbles and boulders. And talus, for the most part, tends to be very stable under your foot, other than the occasional wobbly cobble. Scree is loose rock under your foot. It is much smaller, so smaller cobbles, maybe even some pebbles. When you're walking in a scree field, it feels like you're sinking into sand almost. Debris cones are accumulations of material moved in a debris flow. So it looks similar to a talus cone, but the mechanism of formation is a different process. We have rockfall in talus cones and debris flows in debris cones. Again, we'll talk more about those processes in our next lecture. Last, we have block fields. Block fields are large expanses of coarse and angular rock rubble found on plateaus in mid and high latitudes, which indicates that we can expect a frost weathering process that causes these block fields to form. They don't originate from mass wasting. They originate from water penetrating into fractures, freezing and expanding, and growing those fractures, breaking off individual chunks of rocks. So talus cones are going to exist below some vertical cliff face or near a steep mountain ridge. So we have rock fall occurring up here, and it's settling in this cone shape. Block fields, which are also called Felsenmeer, occur in much flatter areas, so low relief. We don't have any cliff to provide this material through rockfall events. So instead, these rocks are being broken up by processes that are occurring within this field of rocks. Duricrusts are a hard mineral crust or coating that forms at the surface or near the surface of soil when groundwater is enriched with specific mineral evaporates. So mineral evaporates are solid minerals, solid molecules that are left behind when water evaporates. Here's a list of the most common duricrusts. We have ferrocrete, which contains iron, calcrete, calcium carbonate, silcrete, silica, alcrete, aluminum, gypcrete, gypsum, magnacrete, manganese, and manganacrete, that's a hard one, or magnesite magnacrete, sorry guys. Different types of these duricrusts form in different climates. The duricrusts, once they form this hard, thin layer that tends to be harder than the materials in which they occur. So they'll form in soils, fairly unconsolidated soils, and now we have a hard layer within that soil that's going to be more resistant to erosion. And it can form inverted relief, similar to the idea of inverted relief forming from basaltic lava flows. So here, this diagram is showing an example where we have a valley and we have a duricrust forming in the soil within that valley. Over time, the valley walls are subject to weathering and erosion, and they are less resistant to those processes than the duricrust itself. So the valley walls are eroded away, they decrease in elevation, and now the duricrust-filled valley sits above the valley walls. So we've inverted the relative position of the duricrust between stage 1 and stage 2. Desert varnish microlaminations are a type of duricrust that form in arid climates. They're primarily composed of clay, which is transported through blowing winds, iron oxides, and manganese. We have colors ranging from brown to black. Now, this video will be linked, Zion National Park Desert Varnish. It's a very informative video, but I'm not going to be able to show it during this recording. So please watch that after you're done watching this lecture. So now, to bring everything together, we talked about our two main types of weathering processes, chemical weathering and mechanical weathering. So where are these processes occurring most frequently in relation to climate? If chemical weathering is dependent on the availability of moisture and high air temperatures. So we experience high rates of chemical weathering in tropical climates. It's minimal in dry regions because we don't have a sufficient water source, and in cold regions, which might contain water, but that water is frozen. Mechanical weathering is also dependent on the presence of water, but now we also need some temperature changes to initiate that expansion and contraction. So we have high rates of mechanical weathering in temperate and polar climates. So example, freeze-thaw is only possible in temperate and subarctic regions. We're not going to get freeze-thaw cycles dominating in the tropics. So this graph, we have temperature, mean annual temperature on the x-axis, and precipitation on the y-axis. So we're looking at water and temperature. Chemical weathering is going to occur where we have high rates of precipitation and high temperatures. So where's my mouse? I lost my mouse. There it is. Weak chemical weathering, we have low precipitation, low temperatures. Strong chemical weathering, we have high precipitation and high temperatures. Now look at mechanical weathering, where it's the opposite, where strong mechanical weathering is moderate precipitation but very cold temperatures. And look, it's absent or insignificant at these higher temperatures, regardless of what that precipitation rate is. Now this chart, or the C graph, is just a combination of A and B. So we can now look at the differences in color and see where we have some overlap. So moderate chemical weathering with frost action can occur within this region. So we have a water source, we have moderate temperatures, and again we're looking in Celsius, so the freezing point is down here. So freezing in this region of the graph, we can have some frost action. Over here it'll be minimal, but we'll start to experience some chemical weathering as well.